Hey, good morning. We're going to continue on with Chapter 6 today, and we'll also be talking about Chapter 6 Wednesday, so try to read the last couple sections. We have homework that's due on Friday, and we talked about a lot of the problems. Hopefully we'll talk about the last two problems today. I have an exam a week from Wednesday, and one of my goals for this afternoon is to get your practice exams out to you. So that should be out within the next few hours. All right, if you haven't gotten your homework, I have homework number 5 to hand back. You can come get it after class. Okay, so today what I want to do is we talked a lot about the Hodgkin-Huxley model and how it's a nonlinear model with gates opening and closing. I'm going to simplify things today. I'm going to represent the membrane as a simple capacitor and resistor, a fixed resistor that doesn't change, just one. But in return, I'm going to take into account what happens with space along the axon rather than assuming it's just the same everywhere along the axon. And we'll get what's known as the cable model. And in next class, we'll put it all together and see what it has to say if you have both. So let us begin with just having outside, inside, and all we have is your capacitance and a conductance. And even more, we're ignoring any sort of Nernst potential, so we're really going to measure voltages with respect to rest. So this is going to be the membrane when we're measuring all our voltages with respect to rest. So C is really the membrane capacitance per unit area. So it has units of farads per meter squared. And G is going to be the conductance of the membrane per unit area. So membrane conductance.
Looks like a resistor.
It looks like a resistor, and if you just take the reciprocal, you will get the resistance times unit area. But it's somewhat easier to use conductance because then you get per unit area, which seems to make a little more sense. It's analogous to the capacitance. So conductance, resistance, really inverse ideas. So then if you want to get the current density through the membrane, well, these are all per unit area. So the current density, Jm, is just going to be C dV dt. And this is going to now be a partial differential equation because we're going to take into account time and space along the axon. So partial derivatives plus, and here's where the big simplification is, just G times V, which is really Ohm's law, V equals IR. So it's really V over R if you want to talk in terms of resistance. So the membrane's much easier. But like I said, the price we pay is we're now going to have an axon that's distributed in space. And the axon is going to have a radius, A. So A equals axon radius in meters. And the axon has salt water inside. And salt water has its own conductivity. So I'm going to make sigma be the axon conductivity. That is of the intracellular space. Conductivity. And conductivity has units of 1 over ohm meter. And again, if you wanted to talk about in terms of resistivity, it's just the reciprocal of conductivity. All right, so first step is we have to look at what happens if we have voltage gradients along the axon. And if we do, we're just going to use Ohm's law. V equals IR is a simple way to write it, but there's another way to write Ohm's law, and that is the current density, and this is Jm, the membrane current going across the membrane. This is Ji, currents going down the inside of the axon. And that's just going to be sigma times the electric field inside the axon. And the electric field inside the axon is just going to be minus the voltage gradient, or minus the derivative of the voltage, So you get minus sigma dV dx. So the intracellular current depends on voltage gradients. If the voltage was the same everywhere in X, there'd be nothing driving the current. There'd be no voltage differences to drive a current. This is a minus sign just from standard electricity. Is usually electric field is minus the gradient of the voltage. And there you have it. So that I would call Ohm's law. It looks a little bit different than V equals IR, but really it's not, because there's V, voltage difference, and this is really a current density, and here 1 over this would be a resistance, so it really is V equals IR. Okay, so, and notice the units work. Let's see here. We have a voltage times a conductivity. So we got 1 over volts over ohms is just an amp. And then you have a 1 over meter here and a 1 over meter from the derivative. So it's amps per meter squared. So it is a current density. Next thing I want to do is I want to look at a continuity equation. Let me point out one more thing about this before we go. This should look very similar to what we've done before. We have done diffusion, where we had the molecule current density was a diffusion constant times the gradient of a concentration. We did heat, we did forces is gradients of pressure. So this should all be very familiar. Now let's look at more of a continuity equation. Let's look at a little piece of this action. Length delta x. So this ends here is at x, and this end is at x plus delta x. And what we want to do is we want to basically use Kirchhoff's node rule. We want to use that the current in is equal to current out. So how much current's going in? Well, on this side, we have a Ji at x. That's a current density. So in order to get the total current coming in, we have to multiply it by the area. Cross-sectional area here. We could also have current going out. And this is Ji at x plus delta x, again times the area. Now, the current, those two don't have to be the same, because there's one other thing current can do. It can cross the membrane and come out of the cell. So, if you have current coming out like that, that's the Jm. And if you want to know how much total current, you have to really take Jm times the cross-section, the surface area. So the surface area is going to be delta x, the length, times the circumference, 2 pi a. If I cut this and set it out flat, it would be a sheet of width delta x and length 2 pi a. Okay, so we're almost there. This is a continuity relationship, so let's just add them up. The total current in is equal to the current going out. So in other words, Ji x pi a squared going out is a minus Ji x plus delta x pi a squared, and going out is minus Jm x delta x 2 pi a. All those have to equal 0. So guess what we're going to do now? What's the next step? What's the next step that we've done in all these other examples? Turn it into derivative form. We're going to make it a derivative. And what do we need to do to get it into a derivative?
Divide by delta x.
We'll divide by delta x. We might as well go ahead and divide by this whole thing. Delta x times 2 pi a, but the one that's crucial is dividing by delta x. So, I'm going to put this term first, so I'll factor out the minus Ji x plus delta x, and then you're going to get this term, but now it has a minus sign, Ji of x, and you divide it through by delta x. So what else do you have? Well, these two had a pi a squared, and we divided by 2 pi a. So that term takes care of these terms. All that's left over here is a Jm, which will move to the other side and make it positive. And what do we get? The pi's cancel, one of the a's cancel, and you're going to get a over 2 times minus sign dj dx equals jm. So this is a continuity law. I might as well be putting i's on these. So that's ji. So what it's saying is the only way you get current coming across the membrane is if you have more current or less current coming in from one side than out the other. If you had the same amount of current coming in from both sides, there couldn't be any current going out the membrane. Okay, so we got two relationships now, Ohm's law and a continuity relationship. I might as well put Ohm's law here in a nice box too. They're boxing one and not boxing the other. Okay, so I just rewrote this. Forgot the middle step. Now, what do we do next? We want to get an equation for voltage. Well, we have an equation for Ji. We have an equation for Jm. And we have this continuity relationship. So let's just put this in for Ji. And let's put this in for Jm and see what we get. We're going to get a minus A over 2. This is a derivative of, there's another minus, so I'll make it plus, and there's a sigma. And there's a derivative of V there, and there's another derivative, so you get two derivatives. So the left-hand side is going to be this. And the right-hand side is just going to be what we have up there. C dV dt plus GV. Now the usual thing is to do at this point is to divide by G. So you get A sigma over 2G d squared V dx squared equals C over G dV dt plus V. And this is basically the cable equation. So, what you'll usually see is it's written slightly differently. Usually you're going to define this as a constant. And it's usually called lambda squared dV dx equals, and you define this thing as a constant. And what's usually done is, this is like C over G, that's like RC, that's like a time constant. So it's usually given tau dV dt plus V. And this is the canonical form of the cable equation, where lambda is the square root of that, A sigma over 2G, and tau is C over G. So this will be one of our key equations for the next exam. You want to know, or at least remember the cable equation. It looks a lot like the diffusion equation. We derived it a similar way. So questions about how that was derived. It's only true for a constant membrane. Eventually we'll replace this term with a term that has all the opening and closing of the gates. Okay, so now when you have an equation like this, it's kind of complicated. The best thing to do is to start looking at special cases. So let us look at some special cases, and I'm going to erase this whole big thing, and then we're going to move on. So we'll keep the cable equation. All right, so we're going to look at the cable equation, and we're going to look one by one what happens if certain terms are small. And the first case is we're going to assume this term is small. So, 1, if V is small, And what do I mean by v? I mean small relative to these other terms. So maybe the length constant and the time constant are really big, or these derivatives are big. So we're going to assume that for whatever reason this is a small term. And what do we have left? We have just those two terms. What's that equation? Two derivatives in space, one in time.
The cable equation?
Pardon?
The cable equation?
It's the cable equation, but without this term. But does that look like anything we've talked about before? Two derivatives in space, one in time. That's the diffusion equation. When we talked about the diffusion equation, all we have to do is divide through by, see, I usually put the d right here, by tau, and you're going to get d squared d dx squared equals dv dt, where d is lambda squared over tau. So what you essentially have, if this term's small, you get the diffusion equation. And that means that, in some extent, diffusion plays an important role in nerve axons. Basically, voltage, or you can think of it as charge if you want, but voltage diffuses along the axon. And its diffusion constant depends on this constant here. It has units of distance, and this constant here, units of time. So diffusion is going to play an important role. In fact, when we talk about how action potentials propagate along an axon, they basically diffuse down an axon and then trigger another action potential downstream. So it's going to be crucial for how they work. But that one's rather simple case. Let's look at another case. Let's look at the space clamp. Okay, space clamp means things don't depend on x. Well, that's what we did before. If things don't depend on x, this term here goes to 0. And all you got is these two terms. And that's now a really simple equation, because if nothing depends on x, you can solve this for v. You end up getting a total derivative because nothing depends on x. You just get a minus v over tau if I just solve this for dv dt. And it's essentially a decaying exponential. So another property of the cable equation is voltages, deviations from rest, tend to decay away with time constant tau. All right, so this term's kind of boring, but I want to show you what happens if you add in another twist. You add in a stimulus current. And then we're going to look at stimulating nerve axons. So this is going to be now problem 6.37 in your book. Talks about stimulation. So we're going to go on a little bit of a digression. 37. A little bit of a digression solving this example in the case of a stimulus current. If there's a stimulus current, that means you're going to pick up a source term in addition to all these. You're also going to have a stimulus source. So your equation is going to be the same as before, plus there's going to be a source term. I'll just call it a source S, and it's going to be a function of time, and it will be proportional to the stimulus current. Well, we won't worry too much about the units right now, but you're going to get a source term. And this source term, what we're going to do is we're going to turn it on and off like a square wave. So in other words, if you look at the source term as a function of time, we're going to, at time 0, we're going to turn it on, and it's going to have a strength S0, and at time D, we're going to turn it off. So you're going to be stimulating with a square wave. And now what our goal is we're going to try to figure out how strong of a stimulus you need and how long of a stimulus you need in order to stimulate the axon. So, what do? Well, we're going to have to solve this differential equation. This thing is it's a constant term, which is either S0 or it's 0, depending on what time you're at. So, we have done this before. If you have this term, you just get exponential. If you have just that term, it's a constant. So we're going to guess. So our guess will be the voltage is A plus B e to the minus t over tau. That seems like a reasonable guess. Now, that's what we're going to guess in this region between 0 and D. Before time 0, it's just at rest. There's nothing happened. So the voltage was 0 all up out here. That fits this equation. It's a simple result. V equals 0. At time t, we start like this. What do? We stick that into our differential equation. What is the time derivative of this thing? That's a constant. This gives you a minus tau, so you get a minus b over tau e to the minus t over tau. That's the time derivative of v going into here. Equals, and here we get a minus v over tau. So a minus a over tau, and then we get a minus b over tau, e to the minus t over tau. And during this time, because this is really true from 0 less than t less than d, you just get a constant S0, so plus S0. How can we simplify this? Well, fortunately, these two terms are exactly the same, and they cancel out. And that means that we can just immediately get A, because this side is 0 now, so A is S0 tau. So we've already gotten the A term. So our guess now becomes S0 tau plus B e to the minus t over tau. How are we going to get B? Anybody got a suggestion for how we're going to get B? Somebody must have a suggestion. I'll just pick on somebody. Greta, how do you going to figure out B? I'll give you a hint. What happens? What's this equation? What should it be at time 0?
At time 0, it should be that should be to 0, which is 1.
Okay.
So we just have as b equals 0 tau plus b.
Okay. S0 tau plus b, and what should this side be at time 0?
Yeah, so that's 0.
0, because this has to be a continuous equation. So this has to be 0. So now we have everything we need to get b, and in fact b is really simple to get, minus S0 tau. So now our solution is now A, they both have S0 tau. A is 1, and then you get a minus e to the minus t over and tau. And this is the solution in this regime right here. It's going up towards S0, heading up towards that. If it had continued, it would have gone up to S0. And then once you get past that, you turn the stimulus off, it's just going to decay away with time constant tau. And we won't even try to work out the expression for that. We know it's going to decay away. So this is the solution for the cable equation. Now we're going to do one thing beyond our simple cable equation. We're going to say that if this solution gets up to a certain threshold value of voltage, you're going to stimulate the nerve. And if it doesn't reach that threshold, you're not. So this is sort of like saying it has to reach the point where the positive feedback loop starts in and you get your action potential. But we're going to simplify things and say that's just a constant. So its peak value has to be equal to that constant or above it in order to stimulate. So where's the peak? At what time do we get the peak value? That's pretty clear that's going to be at time D, the duration of the pulse. So what we're going to say is there's some threshold voltage we have to reach. And it has to reach that at time 1 minus e to the minus d over tau. And if we do, or we get above it, we'll stimulate. So this is going to be where you just barely stimulate the nerve axon. Okay, so this is really what's known as the strength duration curve. You want to know the strength, that's this S0, how hard you're stimulating. And D is the duration of the pulse, and it's a relation between the two. And you can actually solve this for S0. This is the usual way it's done. It would give you a V threshold, which is some known amount, probably around 10 to 20 millivolts, divided by the time constant, and then 1 over 1 minus e to the minus d over tau. And that's known as the strength duration. This is the expression, but you can think of it as the strength duration curve. Okay, so let me get this taken care of. All right, so what I want to figure out now is what sort of stimulus do you need for different durations. So let's see what happens. Let's plot this thing. Let us plot strength versus duration. Well, if you have a very long stimulus, so D is very big, this becomes e to the minus a big number. So that's going to be negligible. And you just get V threshold over tau. So for very long D, this goes to V threshold over tau. That's how strong you have to stimulate. And it's coming in here flat there. How about if D is really small? Well, this one's a little harder. If D is really small, e to the 0 is 1, 1 minus 1 is 0, you get 1 over 0. Well, that means it's going to get really big, but let's see if we can do a little better than that. How are we going to try to do better than that? What can we do with the exponential?
Use the Taylor series.
We'll use the Taylor series. E to the minus d over tau for D small is approximately 1 minus d over tau. That's the Taylor series expression. So if we plug this in here, we get 1 minus 1, so there's your 0, but we still have this term left, a minus and a minus. You get a d over tau here, or in other words, tau over d. The tau will cancel that tau, and you'll get S0 equals V threshold over D. So the threshold voltage will come in. I made my curve bad because it's going to come in going really high and then fall off. That's the 1 over D curve. So the actual strength duration curve is going to look something like this. It's going to go up. It doesn't go to it. It goes up to infinity right here. If you stimulate with a strong stimulus, it just takes a constant stimulus. But if you stimulate with a real short stimulus, you have to get stronger and stronger because of the short duration. So we can kind of see this happening if you look back at the voltage as a function of time. So if we plot voltage as a function of time, 0, D, if D is a lot larger than tau, this thing will go up almost immediately and then be flat until it finally comes here back. So it doesn't really matter if you make D longer. The voltage has reached its peak value already. So making D even larger doesn't help you any. That corresponds to the flat part of the strength duration curve. But if voltage T 0 and now D and now the time constant is going to be real long, it'll come up here and it'll start going up, but it goes up slowly because of the long time constant, and it never even gets close to its asymptotic value before it reaches its peak and then starts falling back down. So you see in this case, if you made D longer, your voltage is going to get higher, and it's almost in proportion. So when you're really short stimuli, it will can pay to make the stimulus to duration longer. All right, now there's some special words that are given to these. Let's see, I need some more space. Anybody have any questions so far before I raise? Yes?
Originally you had a towel, the differential equation in the beginning.
Uh-huh.
And your guest also had a towel. And
Yeah.
then at the end they canceled.
Yes, if I wanted to, I could have, in my guess, I could have made my guess something besides a tau. I could have just had it T over, C. And I would have eventually shown that in order for these two to cancel out, C had to be tau. So I kind of took a shortcut. But yes, in general, you would have to put in some sort of exponential behavior and then show that really C is tau. Other questions? Okay, let's see. So here's going to be get a better picture of the strike duration curve. The S0, here's going to be your V threshold over tau. And the curve looks something like this. Now, there is a name for a couple of these stimulus, for the stimulus strike. The stimulus strike that corresponds to a real long stimulus is called the Rio base. So imagine you have a stimulator, it has two knobs on it. It has a duration knob and a strength knob. So what you do is you set the duration knob real long. And then you start increasing the stimulus knob. When you increase it just enough to get an action potential, that's your Rio base action potential. So Rio base has units of whatever the stimulus is. Then you take the duration knob and first of all you take the stimulus knob and you set it to 2 times V threshold over tau. And you start reducing the duration knob until your stimulus goes away. And that is called the chronaxy. Chronaxy is a duration that corresponds to a stimulus of twice Rio base. So these two terms, Rio base is a stimulus strength, chronaxy is a time. So it's in milliseconds. Those are the two parameters that, if you're just in the lab with your stimulator, characterize the strength duration curve. They can be easily measured. Again, you just crank up your duration knob real long and increase your stimulus until you get an action potential that's your Rio base. Double it, and then start reducing duration until your stimulus goes away. Chronaxy. Okay, we can actually relate that to some of the parameters. For instance, we can try to figure out what tau is. Well, if you want tau, we can go back to our original expression for the stimulus strength. Okay, we set the stimulus strength to be twice V threshold over tau, or V. That's the stimulus strength on the strength duration curve. Equals, that's twice Rio base, equals V threshold over V times, that's just this, times 1 over 1 minus E to the minus D chronaxy over tau. What I've done is I've gone to my curve. Actually, I think I should set this to be tau. This is the Rio base. The Rio base is this V threshold over tau. Twice Rio base is here. So I've set the stimulus strength equal to twice Rio base, and I'm figuring out what the chronaxy is. And the nice thing is that these two cancel. And I've got this complicated thing in the denominator, so I'll just take the denominator of both sides. 1/2 equals 1 minus E to the minus V chronaxy over tau. Then you can solve for the chronaxy. And I'll leave that a little bit to you. You're going to get this logarithm of 1/2 again. You're going to end up getting that the D chronaxy equals 0.693 tau. There's a couple steps missing in here. You can fill them in after class. What that means is that you can do this trick of measuring the chronaxy just by doubling the stimulus current and reducing the duration, finding the chronaxy. And once you have it, you can figure out what the time constant of the nerve axon is. And they're both proportional to each other. So you can learn a lot from this strength duration curve. So this is what people use all the time when they're doing electrical stimulation. When you do electrical stimulation, you're trying to restore somebody with a neural prosthesis where you're trying to stimulate nerves so that they'll activate muscles and automatically work their arms, or with a cochlear implant will stimulate and restore hearing. It happens all the time. These are some of the basics involved. We'll talk more about those applications in a later class. Okay, let's get an idea of how long this time constant is. C. We said C was about 1 microfarad per centimeter squared. Or if you do the conversion, is 0.01 farads per meter squared. And G, you're actually going to calculate G in one of your homework problems. You're asked to calculate the resting membrane conductance. And you're not going to get exactly this result, but it's going to be pretty close to 1 over kiloohm centimeter squared, or millimole centimeter squared, which if you do the unit conversions is about 10. 1 over ohm meter squared. So the time constant is C over G. In other words, RC, if you just take the reciprocal of this. And so that if you take the reciprocal of G, you get R, which is a tenth, times C, which is 100th, you get a thousandth, 0.1. And you get ohm farad, RC, it's just a second. Or in other words, 1 millisecond. So the time constant for a nerve is on the order of a millisecond. So if you're ever stimulating to stimulate nerve axons, you're probably going to be using a stimulus duration on the order of a millisecond. You could do it a little shorter. You can go up the strength duration curve. You could do it a little longer if you wanted to. But millisecond is sort of typical time that nerves work. Okay, so that's a little bit about the space clamp case. Any questions on that case before we move on? All right. What's the next step? The next step is to get rid of all this. And we have a third case of the cable equation we have to look at. Okay, we looked at the cable equation. Yeah.
There's just one thing I don't understand. The original one where we could set V equal to 0 and get the diffusion constant. That was when we were taking the derivatives of the concentration, not the voltage.
Yeah, but it's the same differential equation. So what it's saying is that voltage acts a lot like concentration in that situation. It obeys the same differential equation, so it's got a lot of the same properties. Okay, we looked at when this term was small, just the one you were talking about, we got a diffusion-like equation. Then we looked at the space clamp case. So the next thing to do is to look at when this term's small. That's the steady state case. So we're going to look at 3 steady state. Steady state means the time dependence has gone away. Things have reached an equilibrium. So we'll set that term to 0. And what we're left with now, we can use total derivatives because there's no time dependence. And that's going to give us a V over lambda squared. Okay, now I told you basically when this is gone, when this term was gone, this was just a time derivative as V. That's an equation we've seen many times. Haven't really seen this equation too much. Anybody know what the solutions are to that equation? second derivative is proportional to? What function has its second derivative proportional to v? Sine and cosine is a good guess, and it's almost right. The thing is, if you took a derivative of a sine, you get cosine. If you took a derivative of cosine, you get the minus sign. If there had been a minus sign out here, that would have been exactly the solution. But there's not. So what's left? What other function is proportional to its second derivative? Pardon? Yeah, it is going to be an exponential. The exponential not only is proportional to its first derivative, but also to its second. So we can guess a solution. And it turns out there's two solutions, plus or minus x over lambda. Either of these solutions, if you took two derivatives of it, you get two factors of lambda down here. 1 over lambda would just be what's needed. Even if you had a minus sign, two derivatives would give you two minus signs. You get the plus minus sign. So there's two solutions, so that's a little confusing. But it's the second order differential equation. Second order differential equations, if you go to a math differential equation class, you'll find they always have two solutions. So we can get some linear combination of these solutions. All right, so what I want to do is I want to look at a case now where we have our nerve axon. And it's a real long axon, so we can ignore the ends. And this is the x direction. And at x equals to 0, we're going to stick in a little electrode. These are one of those electrodes that you can has a real small tip, and you can poke it right inside the axon. And we're going to use that to set v is equal to v0 at x equals to 0. So we're going to hold the voltage, just at, say you're trying to do a voltage clamp, but we're just going to voltage clamp right at x equals to 0. And what we want to do is we want to figure out what happens to the voltage along the axon. Okay, well, we have to get v of x. And there's really two cases. X is positive and x is negative. So I'll write it as two cases. One for x greater than 0. Well, we get some linear combination of these two solutions. But if the voltage is growing with x, that would be nonsense, because it would be going off to infinity at the end of the axon. That can't make any physical sense. So as a physicist, I'm just going to say we throw out the plus sign. And we only have the exponential, the decaying exponential. So you're going to get some constant times e to the minus x over lambda. And what's the constant? Well, when x is equal to 0, it's got to be v0, because that's how we're holding it. Now, if x is less than 0, well, now if you had a positive x, and you went clear out to minus infinity, well, let's suppose for a moment you have a negative x, and you went out to minus infinity, you would end up having e to the huge number, be going to infinity again. So you throw out the negative sign in this case, and you get e to the plus x over lambda. So the solution looks something like this. This is v, this is x. It's going to be even function because there's nothing to distinguish right from left. It's going to be equal to v0 right here at the center, and it's going to decay away to 0. And I've sort of done that with a little bit of hand waving, but that's the solution you get if you more rigorously came up with a guess and figured out the linear combinations. Now, how fast does it fall off? Well, it falls off to 1 over e, so about 1/3 of its value at a distance lambda. Lambda is a distance. So lambda tells you how fast this voltage is falling off with distance. If you go out several lambda, the voltage is utterly negligible. So just like tau told you sort of the time scale over which nerves work, lambda tells you sort of the spatial scale over which nerves work. So let us see what lambda was. So look back in your notes. Lambda was, I believe, a sigma over 2g square root. Well, we have to figure out a specific nerve. So we're going to use a nerve that's about 10 microns in radius. 20 microns in diameter. That's a pretty good size nerve axon for humans. And sigma, that's the intracellular conductivity. That's just salt water. And if you measure sigma, it's on the order of 1 over ohm meter. And we already said that G was about 10, 1 over ohm meter squared. So we'll put these values in. 10 microns, that's 10 to the minus 5 meters, times sigma, which is 1 over ohm meter, divided by 2, and G is 10, 1 over ohm meter squared. Okay, the ohms cancel. You get meters squared up here, and you get 1. Whoa. Okay, that meter cancels that meter. This 1 over meter squared comes up, and so you get meters squared for the units, but it's in the square root. So the whole thing will turn out to be meters, which is as it should be. Here it is 10 to the minus 5, divided by 10, I'll give you 10 to the minus 6. So you're essentially getting 1/2 times 10 to the minus 6 square root in meters, once you do the units. And 10 to the minus 6 square root just gives you 10 to the minus 3. So what you're going to get is times 10 to the minus 3, which is milli. And square root of 1/2 is going to give you around 0.7. Then millimeters. So the typical distance over which nerves work, it's on the order of a millimeter. So nerves work at a time scale of a millisecond and a spatial scale of a millimeter. And that's basically what we learned from this example. If you stick in an electrode, you'll find the voltage will decay over a few millimeters. That's got some implications. If you stimulate a nerve way up here, say in your, let's say you stimulate a nerve in your hand. You probably wouldn't want to do this experiment by sticking electrodes in your body, but if you did and you stimulated, well, if all we had was this electrode, this model, your brain wouldn't see anything. It would have decayed way away. We'll find out next class that you can send signals. We have to give up that assumption that the conductance is constant. It says that if you divide a nerve up into little sections, which is what it does with myelination, if you're little, and so there's little active spots that fire action potential separated by just sections that look like this simple nerve axon that are passive. If those spots are several millimeters apart, then when one fires an action potential, that signal will decay away and it can't fire another. You need to have your little hot spots in a myelinated nerve closer than, say, a length constant. We'll talk more about myelination later. But it tells you how far these voltages transfer down the nerve axon. Okay. One more thing I wanted to show you on this example is we can also get something that's called the input resistance. We want to figure out how much current. Suppose you know that you're injecting current I0, and we want to figure out how big the voltage is right here at the center. So you don't specify V0, you specify I0, and you want to figure out how big V0 is. So you really want to get some idea about effective resistance for this axon. Well, one way you can do it is you can calculate the current going down the axon. So here's the axon. Here's the electrode. Injecting current I0. And where's that current going to go? Well, half of it this way, half of it that way. But some of it will go this way and then cross the membrane. And some of it will cross the membrane rather quickly. And there's this voltage, this current crossing the membrane in steady state that's causing the voltage across the membrane. But right here at x equals to 0, if we could figure out how much current was flowing, say to the right, before any of it has a chance to cross the membrane, that's half of the total current coming in. It's half because there's current going left and current going right. So, I0 is going to be 1/2 of the current going to the right, which is going to be current density times area, pi a squared. The current density is going to be Ji, which is sigma dV dx. That's basically the total current going to the right here. And I have a half because it's only half of the current that's coming through the electrode. And we can calculate this. dV dx is going to be a minus V0 over lambda. I'm not going to mess with the minus signs because I think there's supposed to be an overall minus sign. But let's just find out the magnitudes. Okay, so you're going to get from this derivative V0 over lambda 1/2 pi a squared sigma. So if we make this V equals IR, we get I0, let's bring everything over to the other side, equals 2 lambda over pi a squared sigma V0. And this quantity, got my 2, I had my 2 in the wrong spot. No, I think I'm okay. This quantity here is what we call the, well actually the reciprocal of it is going to be, it's 1 over R input. Because if we brought this to the other side, it would be a resistance, V equals IR. This is what's called the input resistance, and that tells us how much current you have to inject into a nerve in order to get a certain voltage. So why is this useful? Suppose that we said, well, in order to fire an action potential, we need to make the voltage right here at the center 10 millivolts. Well, 10 millivolts is the amount that would then trigger the positive feedback when you get an action potential. So you can calculate the input resistance, and that would allow you to calculate I0. I0, and I'm not going to do all these calculations, you end up needing nanoamps of current. You don't need to inject much current. But it acts like you have mega ohms of resistance if you calculate your input resistance. So it gives you a little bit more information if you were going to go stimulating nerve axons, how much current you need to use in order to trigger action potentials. All right. Last thing I want to talk about today is a couple of the homework problems. So we're going to talk about those last, well, we're going to talk actually the last two I think we've already done, but the 28 and 35 are the ones we haven't done, I believe. Any questions here before I erase them? Yeah.
How did the 2 get on the top?
I'm wondering, did I screw up or did I, because I moved the I0, how did the whole thing get on the top? This is, okay. What I did is I took my reciprocal twice. Let's see, how did the whole thing get on the top? This is going to be, I'm sorry, pi a squared sigma over 2 lambda. And that is 1 over R input. So R input would be 2 lambda over pi a squared sigma. In my head, I was going after R input, and I did the reciprocals twice. That's right, isn't it? Because V0 is, and even then, I'll have to double check the 2. I'll check it and let you guys know. I have a feeling that I messed up even back here, because you really want this to be half of the total current going in. I will check this 2 and let you all know. So that's a note to myself. Okay. Let's go on while we have time and talk about problems 35 and 28. Okay. Okay, 35. In your homework says the cable equation, it gives you the cable equation. Let V is equal to W e to the minus T over tau. So basically, you have your cable equation. a little bit different order. But we're going to do a guess, just like we've always done. But we don't know anything about what's going on. So we're just going to know that, okay, sometimes the cable equation acts like it has an exponential decay solution. So we're just going to guess that. We're going to say v of xt is equal to some other function called wxt, and then you have your minus exponential decay. What I want you to do then is to stick this guess in for v and find out what happens. And basically what you're going to find is you get a new differential equation for w and see if you recognize that differential equation. So that's really what the problem is asking you to do, is you can't solve it completely and figure out what w is, but you can at least solve for a new differential equation for w. So give that a try and see how it goes. And as usual, we're going to have time for questions on Wednesday if you're stuck on any of these. Then the other one's problem 28. Problem 28 says, okay, suppose somehow you know v as a function of x. This is kind of a rough picture of what it looks like during an action potential. And what it asks you to do is to plot the current along the axon. So you're trying to figure out what current is flowing along the axon. And I'll just kind of give you a hint. Well, you know that the intracellular current density is minus sigma dV dx. So in regions where dV dx is going to be flat, you're getting zero current. Where regions where dV dx is increasing, and this is nice because it's a straight line, where dV dx is increasing, you get a constant current that's actually going to the, has a minus sign here to the left. So you're going to have a current going this way. Where dV dx changes sign, so now it's constant, but it's going now down, so it's negative, so the net current's going to the right. You get a bigger current because it's a bigger slope, but over a shorter distance here, and then you're back to zero out here. So if you were plotting the current, you'd find big negative, real big positive, and back to zero. You're asked to calculate, well, basically plot this current and calculate how big these are. So you got everything you need because this is the current density, and the current is pi a squared ji. So you have everything you need to figure out what the current distribution is along this axon. So that's what you're supposed to do. Okay. That should be everything you need for the homework as far as hints go. Yeah, 41 and 43 we talked about. So did anybody get started on the homework and have any other questions so far? Okay. Well, I encourage you to try to get started on the homework and come with questions on Wednesday. You'll have a chance then. I want to say one more thing about the cable equation. Suppose we had a nerve axon and we plugged in, we injected some current, but we injected that current as a function of time. So you have some current that you're injecting, and the current as a function of time is zero, and then at a certain time it's going to jump up and be a constant. You can solve the cable equation. It turns out it's really difficult to solve the cable equation. You have to use some funny functions called error functions, but it is solvable. And you can figure out in the book in figure 6.30 something, the book talks about this solution. And 6.31, I would encourage you to take a look at it. It's not something that you're going to have to do in this class. It's something where you either do it numerically or you do it with some fancy math that we haven't studied. But it is possible to solve it. What you find is if you wait a long time, it reaches steady state and gives you that exponential behavior. If you look at over short times, it's kind of an exponential increase. It's kind of a mix of everything we've talked about so far. And it also has diffusive properties, in that this current will kind of diffuse out until it reaches steady state. So it's a really interesting problem. It's just a little bit more than what we're going to cover in this class. And that is the cable model. Next class, what we're going to do is we're going to take the cable model and the Hodgkin-Huxley model, and we're going to put them together. Now, the bad news, in my point of view, is that we aren't going to be able to solve analytical solutions and problems. So we're just going to be more qualitative in how it behaves. But the good news is that it will tell us how nerves actually send signals down their axons once we put those together. Okay, if you haven't gotten your homework back, I have it up here. Otherwise, I will see you on Wednesday.